Our seminar today is actually the second seminar this year. There's more of these coming up. Uduak from Mechanical Engineering Department. Before here, he was at Purdue, and then he got his PhD at Rensselaer, and can't seem to find a place with good weather. But let's hear about him with his data-driven modeling for additive manufacturing now.
Thank you. Good afternoon, everyone, or good evening, I guess. Thank you very much for coming out for this talk. So I want to talk about physics-guided data-driven modeling or control in additive manufacturing. So AI and machine learning is all around us, you know, from smartphones and driving. Well, now many systems are becoming increasingly complex or connected and complex, and machine learning is good at learning complex dynamics. And so we can use machine learning to help us to learn complex behaviors or help us make better measurements in the increasingly complex and connected physical systems. Okay, so.
Can you swap the slides? So.
Okay. Seems to be no option for that.
How to do this? I'm not an expert. Yeah.
Okay. All right, so but we have problems with using the big data approach because generally you need a lot of data. Okay, and in addition, with the myriads of parameters you want to learn in AI, machine learning, big data approach, it's hard to explain what's going on and therefore hard to provide certain certifications. And if you need to adapt your models in real time, it may be difficult to train in real time. Okay, so a big question is, how do we incorporate some knowledge we have about the process into machine learning paradigms to better control or, so to speak, better model and as well control these complex systems. And that's the thrust of my research. But before I go on, I just want to talk about a few areas where I've been working on. So my areas of interest has been at the intersection of graph theory, data-driven methods, and control theory. And mostly I've been working in manufacturing applications, inkjet 3D printing being the one I'm going to talk about today. I've also done some work in laser powder bed fusion. That's the process used to manufacture metals additively, or one of the processes. I've also done some work as well in the area of flow control, mostly trying to cancel out common slinting waves over airfoils. And more recently, I've been doing some work in thermal management, especially hybrid thermal management systems where you don't have just the heat exchanger, but you have also a thermal storage device. Okay, so to illustrate this idea of incorporating domain knowledge into machine learning models. So think about, for example, you have a neural network or whatever, you're trying to train to recognize parallelograms. So you feed it with didactic parallelograms like shown here. So it may learn that you have 4 sides, 2 opposite parallel sides, or it may learn maybe that you have 2 triangles, which is more likely, and one rectangle that makes a parallelogram. And so if that's what is dominant in the learning process, so to speak, the weights of the neural network, if you try to test it out on a rectangle or square, to likely fail on identifying it as a parallelogram. So the question is, how do you incorporate the knowledge that, well, squares and rectangles and rhombusses are parallelograms without necessarily increasing your data size and training it on squares and rectangles? So that's the idea, which is sometimes called in the computer science community neurosymbolic AI. So in this case, if we're able to learn the first part of the 2 options, we can better identify test data that's the network hasn't seen. All right, so I'm going to talk about how I've tried to apply this idea in additive manufacturing, in the additive manufacturing process, specifically Inkjet's 3D printing. I'll talk about the modeling, and I'll also talk about predictive control and some future research directions. So our manufacturing systems in general are becoming increasingly smart. And by smart, I mean, you know, there are additional sensing capabilities to enable us actually do predictive maintenance, automation, advanced design, and energy management. And the smart manufacturing market is expected to grow substantially. At the same time, the manufacturing processes themselves are also becoming increasingly complex, especially with the advent of additive manufacturing. We're able to combine additive manufacturing processes with other conventional processes, which is sometimes called hybrid manufacturing, or we're able to actually mix multiple materials in one monolithic part. The question here is, how do we use data to better understand and control these increasingly complex dynamical systems, given also the increasing amount of sensing capabilities we have? Okay, so I'm going to talk about how we think about doing this in Inkjet 3D printed. It's an additive manufacturing process that's droplet-based. It involves you jetting curable polymers from a nozzle and then curing the deposited polymer. So typically, the video shown here you've had the droplets deposited, and then it's gonna get cured. And after curing, the process repeats. Okay, so this process is important for making parts that are, for example, useful for medical and dental fixtures, compliance features, robots, micro electromechanical devices, and very useful in bioprinting. And typically you carry them out heuristically. So you choose all the parameters, all the right combination of parameters in the process that you want, and hope for the best, right? So the problem is you may have layer height inconsistency. That's what this microscope image here shows. And there are a lot of uncertainties in terms of the droplet deposition. For example, you're meant to have equal droplet volumes here, but obviously there's a large standard deviation if you were to take the mean of the droplets there. So this calls for controlling the process, but there are two perspectives you could think about when talking about controlling this process. There's one, the low-level process parameters control, okay, where you're trying to change or modify process parameters. So like the voltage waveform, pressure, jetting frequency. In our case, we have a piezoelectric nozzle, so the voltage is important in driving the droplets out. It's really hard to actually model what this process parameters exactly do on the output metrics, especially in a way that you can go back, that is from what you want to the process parameters. But several work have used things like iterative learning control, fusing logic, and neural networks to some extent to achieve some extent of relationship between these parameters. But the second perspective you could think about in controlling this process, which is what I'm really interested in this talk, is the geometry level control, where you're closing the loop based on the old part geometry. So you're thinking of from the input pattern I give to the output geometry that's produced. The main thing you need to do here is understand the dynamics of the droplet deposition fraction. It's hard to do, very hard to do. There are finite element models that do for a couple of droplets, but in practice, you're dealing with thousands of droplets. There are linear simplified models, reduced order models that are suitable probably for controls, but do not capture significant nonlinearities. So the idea here was we use a data-driven but physics-guided model that can learn nonlinear fluid behavior, but still somewhat accessible for model-based control. So if we think about our system, let's assume that we just printed a layer L, okay? And we know the reference for layer L plus 1, okay? So for model-based controller, based on YL and RL plus 1, we can generate input pattern UL that would give us YL plus 1, okay? If we're interested in doing feedback control, we feed that back to the system and we repeat the process. So what really we need here is a model that relates the input pattern UL to the change in YL. So YL plus 1 minus YL. And that's what we'll talk about. And I'm going to talk about two modeling approaches that you could use for this. And and the drawbacks with them, and so motivate why we're using a physics-guided machine learning model here. So the first is just to do a linear superposition model. I mean, that's very intuitive. So essentially, you just have a filter, you convolve it over the input space that you're interested in, and add that to your current layer and get. But doesn't work that well. So here, this is a cross-shape part. This is what the linear dynamics would predict for you. This is what the actual experiment. So another approach is to try to do a black box neural network modeling, right? So here, what we do is we feed in the input pattern and the output profile as training data for your neural network. And at least on the training, this seems to capture some of the bulging effect that we see in the actual experiment. I mean, compared to this linear. But on test, doesn't do that well. The performance is rather poor. So the takeaway here is you really need much more data. Okay, and the more data you need, the more you need to increase parameters in your network. And so that's what led us to think about a physics-guided machine learning approach where we combine data but some knowledge about the system modeling. Okay, so that's what I want to talk about now. So if you think about the dynamics here, it's multi-scaled, right? There is a layer-to-layer development, right? And there is also a droplet-to-droplet evolution. Okay, so we've been talking about the layer-to-layer development, but you could think about the droplets-to-droplet evolution. I'm thinking about that. I was thinking about the process from that dimension. You can think about the process as being a recurrent neural network in general. Okay, and what we want to do is we want to build our understanding of the process into a recurrent neural network environment. Okay, so we're going to capture the spatial temporal evolution by saying that let xk, which is the height profile at any time during the process, be the internal state of your recurrent neural network. And you can consider UK, that's your droplets input, at any time to be the input to the neural network. And assuming we need NL time steps to print layer L, okay, you can think of your neural network in this manner. And eventually, the process includes shrinkage. So we have our outputs modeled by g of x at the last time step, because the curing process, of course, after all the deposition have been completed. So that's illustrated here, deposition of UK, dynamics in xk, and shrinkage. Okay, so the first thing is we want to capture the spatial relationship between a droplet deposited and what actually happens when it arrives at the surface, and in a manner that is time dependent. So we can write this. We can write the input here, the input weight UK, as the convolution of BK, filter BK over UK. Okay, so WK then becomes the top least matrix that corresponds to the convolution of BK UK vectorized. Okay, so want to learn the convolution that captures the spatial effect of the deposition. So that's what we have here as the input to the neural network. But here's where the physics guiding is coming in. Okay, so we want to learn that convolutional kernel or filter, but the convolution must be consistent with dynamics that reflects volume conservation, because we know there is volume conservation in the process, and a constrained flow, because we know that there's surface tension constraining the flow of when the droplets interact. And so if you think about the input space as a grid with X there, and say we're interested in this point in red, we can transform the grid points in the domain that we're interested in to links of a graph. And then we apply an activation function that essentially is meant to constrain the flow. And so this is the thresholding function we apply here as an activation function. So whatever, basically we're saying that if the height difference between any two nodes is not sufficiently large, it's in that dead end zone in gray, you don't have flow. So it has to be bigger than that to happen. Okay, so we can write this as we have the input, and then we have this incidence matrix, D transpose acting on the state at any time, multiplied by flowability matrix, essentially saying how much flow will you have in one time step. So we apply this activation function that captures the effect of surface tension. So, and then we take the links back to the nodes domain by multiplying by the incidence matrix again, and that forms the recursion of the neuron. So in all this, we don't know parameters B, F, alpha, and those are the parameters we'll need to learn. So, and then to incorporate or to account for shrinkage at the end of the layer, we use this soft plus function. So it's important to emphasize that we're trying to learn the convolution B, okay, the convolution kernel or filter, but we want it to be constrained by things we know about the process. Okay, so we can write the convolutional neural network in this way, and we can unroll it as shown here. And one big problem with convolutional neural networks generally in training is that the training you could have very unstable gradients. So when you calculate the gradients, if the time step is very long, it could be exploding or vanishing gradients. So in this case, what we're saying is that we're going to train the network based on the data we're storing. Either we're stored, or we even want to be able to train based on data on the fly or online. Okay, so yeah.
So you've got this nonlinear discrete time system, and as I understand it, you're encoding like there's conservation of like the flow that's like encoded as constraints on the F and the D matrix. Is that right?
So,
Is it not, am I not understanding?
yeah, so I mean, that's right. The other thing that we're even doing here is in the selection of what we're using for an activation function, we're making it reflect that, although we don't know yet the parameters alpha, okay? But in addition, so what's interesting is that of course there is condition under which you're gonna have stable gradients, and it turns out it corresponds to conditions for the dynamics as well to be stable. So yeah, so that's what we're trying to do. Okay, so so as I said earlier, training stability is a big concern, and we can show that if we have the big matrix F, okay, to be just the constant times incidence matrix, which is what we do in this case for simplicity. Our system would be stable as long as F is less than 2 over the spectral radius of the Laplacian DD transpose. And you can think about it in terms of this diagram where you have L, the links, and you have the activation function acting here. So as long as you're within the blue zone, you're okay. So I showed the expression for calculating the gradients here of the gradients here of the loss function with respect to the parameters in theta, because what we need is to have this term, this sensitivity term here, to be bounded, okay? And you can actually show that as long as F is within the bounds shown here, this as well will be. So because this term here is rho stochastic, and you can show that eventually the training stability just corresponds to the physical stability of the evolution. Okay, I'll talk about that already. All right, so now we have a convolutional recurrent neural network, and in this case, we train it with just 3 data points, and here's what we have. We have a RMS error that's much lower than that we got through the neural network or with the linear dynamics. But the good thing is that even on the training data, we still have very, very good results with the convolutional recurrent neural network. So this is interesting because with 2 orders of magnitude less data than the black box neural network, we're able to achieve superior results. And it generalizes well across geometries. Okay, I show the cross-shaped part. This is another shaped part. So likely invariant to the geometries used for training. And because we need only few layers of data, it's something we can therefore do even online, as long as training is relatively fast compared to the time step of the process itself. Okay, so now I want to talk about doing control based on the model. Okay, so we've talked about this. So now I want to talk about developing a control algorithm with a model given some data. So as I said earlier, we have 2 time scales, and we've tried to model from droplet to droplet, but we're interested in controlling from layer to layer. So in order to do that, we basically need to take the time dependency away from UK and take it to BK so that we are trying to really optimize with a certain U. And you could do some algebra and eventually arrive at this, that this convolution here is basically equal to BKUL. Well, we already know what BK is, so we can get BK for each time step because we already learned what the actual kernel is. So we can write the dynamics in this way with the matrix BKUL. And our control problem then becomes to get UL that minimizes the reference minus our prediction of the output profile. So basically, it's a reference tracking problem. So what's interesting here is that we basically need the same gradients or most of the same gradient terms that we used in getting the parameters as for the inputs. And we already showed that, well, in training, this term here has a spectral radius that's less than 1, and so it wouldn't explode. So we're sure that when we're trying to get our controller, we're trying to compute for our controller, we'll have we'll achieve a result because the gradients are bounded. Okay, so that is very important because if the gradients are not, you can't really guarantee that you can calculate a controller for the dynamics. Okay, so if we think about it for Z time steps into the future, we can think of it as a model predictive control problem constrained with how much input you can put into the system. You can have negative inputs, and there's a limit to how much you can get. Okay, so and the gradients for all the time steps into the future is just sum of that for each of the layers. Okay, so with this, we can get a predictive controller, and back to the big picture. Essentially, we have our system here, and we're trying to make control decisions based on the physics-guided model given data. Okay. All right, so what we do here is we learn the parameters. So we learn the parameters of the system theta based on a 4-layer cross-shape part. Okay, so we print, we know the input pattern, we know the output, and we use that to get theta star. And then we control based on theta star. So we have a reference, and then we use that to get the inputs. So we do that for the cross shape, a T shape, and N shape part. So right now we're just assuming we're doing feed forward control. We're not doing any feedback. Okay, so on the cross shape and T shape part, you can see that there is substantial improvement in the height tracking, which is what we want. On the N-shaped part, there isn't, and I'm going to come to that in a moment. But what you would notice, and what exactly the controller is doing here is there appear to be these bumps at the edges that it's compensating for, and a lack of alignment that it's compensating. Okay, so if we think about so in the N-shaped part, I just talked about where we didn't have enough improvement. If we think about what was going on layer after layer to see where the problem came in. So at the second layer, so this is using a linear model, these are reference, and this is the conv-RNN. So you can see that the conv-RNN is doing good. It's not doing badly compared to the linear model here. As the layers increase, then we begin to see that it's doing just as good as the linear superposition model. But then with time, it's not doing as well. And you can see the images or the meshes of the part after 6 layers. So what's going on here is that for the other parts we printed, they were thicker parts. And so the parameters that we learned were more attuned with that. And now that we have a thinner part, it's not keeping up. So this suggests that you need some form of feedback or learning, online learning of parameters and feedback during the process. Okay, so and that's what we try to do. So again, we have our cost J, we send in input pattern, and that's the open loop or feed forward implementation. But want to close the loop, send back the high profile information. But in addition, we want to see if we can update our neural network parameters. Well, the problem with this is the training. Okay, so the training could take quite some time, but what we're going to exploit here is the fact that the process itself relatively is a slow process, relatively. But in addition to that, we found a way to cleverly exploit the printing in between layers to learn proactively. But I'll explain what I mean by that in. So let's assume we're trying to print a six layer part, okay? So we compute the control pattern for the first three layers. So we print layer 1, we print layer 2, and then after layer 2, we take measurements. And then we let the process proceed, but then we begin to update the parameters, okay? And we calculate control inputs for layer 4 and beyond, assuming we know what's, I mean, based on model, we assume we know what layer 3 is gonna be, right? So by the time layer 3 is done, we already have the control input for 4 and beyond waiting. And so we repeat this idea over. Okay, so with that, we're able to do a sort of real-time, in terms of the layer, real-time controls using the training, online learning and control. Okay, so with that, this N-shaped part I showed earlier. So you'll notice here that for the conv-RNN alone, okay, this is after the second layer, okay, the errors are basically basically the same. At the 4th layer, they're almost still the same, but the learning and control is doing better because we're learning online and we're doing feedback. Okay. By the 6th layer, we have almost 50% improvement by doing that online. Okay, so, yeah, so to summarize, we've been able to show efficient and effective feedback control with minimal downtime. And within the process, we don't need to have the height profile measured often, okay, because our model is relatively accurate representation of the process. And the computations can be carried out simultaneously as the process proceeds. And this is enabled by a model that captures the dynamics and requires little data for training. Okay, so I will like to acknowledge the people I worked with on this particular project, and also the funding agencies. So in terms of future research direction, there are currently two ways I'm thinking about in this area. So in what I've talked about so far, in the jetting process, we're using a piezoelectric nozzle, and we send in some voltage waveform, and that deforms the channel and squeezes out ink. What this is showing is the pressure distribution with time after injecting the voltage. And then we have a droplet form. So what I've shown so far, we heuristically determine what is a suitable waveform for a good droplet in terms of stability, in terms of speed, or satellite formation. The satellite formation means that you have extra droplets being deposited after the main droplet has been deposited. Previously, we're using a discrete input pattern space. So we calculate our inputs, but we have to discretize them because we cannot online modulate the droplet size. So, but one future direction I'm looking at is being able to modulate that droplet size as the process proceeds. And the relationship between the voltage waveform and the droplets properties that you eventually have is quite complex. And going back from the desired droplet to the waveform you need is an interesting problem. And so that's one of the things I'm looking at. Okay, so the other thing I'm also looking at is, in general, what's droplets spacing combination is optimal from a control standpoint. What this means is this: if you deposit your droplets, for example, too close to each other, there's almost nothing your controller can do. You're just going to have a blob of material. So from a standpoint of how much print time you're taking and trying to as well track the geometry, you want to find out what is the optimal droplet volume to spacing combination. Again, in what we did previously, we used this method that was shown experimentally to really give you good ability to implement controls. But in general, how do you determine what that should be in terms of the droplets, the droplet volume and spacing combination? So I'm looking at doing a co-optimization problem where I'm trying to solve the control problem as well as find what the droplet volume spacing combination is. And with that, I will thank you for listening, and I'm happy to answer any questions. question for a second?
I have a question. So you're printing these things with little drops, like how big do these parts get? I mean, you're talking about micrometers. Can you talk a little bit about what kinds of things you print with this application?
So,
Or it's still just in the basic study phase?
So, okay, so yeah, so the skill we're talking about, well, in this particular setup, we're having about 100 microns in terms of droplet size. The size of the layer is maybe about 30 microns thereabout. But really, so what motivated this application was we're trying to print synthetic organs for surgery applications. And that was when the slide I showed earlier, where you have the layers not uniform. It was that was the case. But the process is used in many other things, including like printing cells for tissues, and it's also used in microelectromechanical devices or sometimes compliance features for robots.
Interesting, thanks.
Yeah, no, thank you for the talk. It was really interesting. I had a question about droplet to droplet variance and volume.
Okay.
And I think it seems like in the future work, you'll kind of get to that with waveform optimization and making sure that all the droplets are stable and no satellites and stuff. But I didn't know if with the current model that you have, if that was an issue that you noticed, or if it's fine, if the droplets seem to have pretty low variance throughout.
I mean, they do have high variance, but if you're compensating from the geometry standpoint of things, it tends to even out. I mean, over time. But yeah, I mean that's a really challenging problem because the deposition of a droplet due to a waveform is very finicky. It's so much dependent on how much the conditions are just right for your nozzle to speed out the droplet. Questions?
A question about the recurrent neural network.
Okay.
So I was imagine the dynamics of different layer will be very different from maybe the base layer to the very high layer. So I was curious about, have you tried use different parameters for each layer? So it's like not just unrolling the single layer of the recurrent neural network, but with the same structure, but different parameter based on the layer. See?
So because we wanted it to be geometry agnostic, we intentionally wanted to learn geometry agnostic parameters. And so that's why we set up the, let me see if I can pull it up here. So the parameters we set up were intentionally such that we wouldn't need different parameters for different geometries. How much we're able to achieve that is a big question. I think we probably need to do more investigation into how much. But I mean, our results have shown good performance. But yeah, so because it becomes rather difficult if you have so many different parameters you're trying to track. But if you can have a set of parameters that are invariant with time or geometry, in time and space, basically, so to speak. Yeah, so you have a better chance.
Yeah, my question is more like, I understand you want geometry across XY plane should be agnostic. You don't really need to know about it, but I was wondering the parameter between the height. So essentially you have unrolling layer of network. And what if each layer has the same structure but different parameter? So
So this is within one layer. This is from time step to time step. Not from layer to layer.
I see.
Yeah.
Just to clarify on that, time step to time step means each droplet, right?
Yeah,
Not like each.
yeah.
So maybe, if you then laid one layer and this is the structure for one layer, do you learn then separate parameters for layer two?
No,
Okay.
so we assume that, so it's, so to speak, I mean, I could continue drawing this RNN on like that, and then after, at n of L plus one, I tap it out again and keep on doing that. I've just drawn one for a layer, but that's, yeah, that's.
In the process you talked about where you print a few layers and then you take measurements and feed it back into the model, what are you measuring? What parameters are you putting back in?
Okay, so here are, right, here are all the parameters I'm learning. So we have the alphas, F, B, V, but let me go to that slide. Maybe it will be helpful to. Okay, yeah, so essentially at the beginning, what I'm just trying, so at the beginning, I assume, or okay, in this case, we did a warm start, if I'll use that word. That is, you identified parameters on something else already, and then you start, okay, based on that to calculate control input for the next, say, 3 layers. Okay. Then after a printed layer, that's the second layer, I go back to now, based on the information I have on these 2 layers, to retrain my neural network. So those and I identify the parameters of theta, which was on the other slide. And based on that, I try to calculate the input, not for layer 3, because I know layer 3 is going on simultaneously as I'm doing the computation, but for the next layer, layer 4, and basically continue the process then.
I guess my question was, I don't understand like what information you're collecting on layers 1 and 2 that you feed back in.
Oh, okay, so it's the height profile data. So basically what I'm using to train is, what did I send into print layer 1? What was printed? What did I, oh, well, in this case, I'm only doing it after the second layer. So basically I'm saying what information was sent in for layer 1 and 2, and what did I measure? So the height profile, we use a 2D laser scanner to scan the height profile. Yeah.
Let's give our speaker another round of applause.
No, I literally checked this more. The man sitting on. You can.
I see.
Check this. Versus
Oh, no.
Man City, Manchester City versus Tottenham. We literally have a beat them at the stadium at like 5 years. Yeah.
So.
Think about whether your course might.
Basically, the one area. Oh.
Yeah, that's kind of more than a year.
My sister.
You know, we do the vibrations one where they
Send me an email.
were right and right whole thing. Wants to use rulers and vibration testing. That's all.
Like a line that's measured. Run over the.
That goes over their heads, I'm sure. but-
Yeah, none of the Gen Z users, anyway, you've got something.
To compare the one paper and the other side.
It was one of the first.
All have this very,
Oh, wow.
So me, I have a substrate.
Oh, that's great.
In the other paper, they complain.
Just, but what I remember, what we're doing was, we had, it had so much resolution. The resolution we were okay with was,
The more experienced.
was 64 points.
It's a big email. What company are you doing your internship on?
Yeah, so we're fine with 8.0, but it could resolve much more.
Email. I do have office hours. I might need to call next week, but because I'm teaching a seminar class for graduate students. So I do have a.
Significant amount of time. Did it add to the build time kind of thing? Was that an issue that?
Yeah, I mean, it does add that, so that's true. There are some other,
Makes sense.
there are some other printers where you can.
No, it's a professional development.
You don't need to move to a separate location, so to speak, to measure. You can measure just longitude.
Are you at the manufacturing seminar?
I'm not so much aware of what they use for that, but I know I recently read work out of MIT, where basically they're measuring institutes. Yeah, but I'm not sure what's being used. Yeah.
That's always the big problem, is trying to do it in real time. Over time, that's.
Yeah, so, yeah, so,
It's a hardware and.
yeah, the down, I feel that if you're able to, so what they were doing in the paper we're talking about, they were actually measuring in real time. We're just doing elementary control, so to speak. So basically.
Maybe I could send you some paper.
It's not as high as it should
Right.
be. You just put a droplet. So nothing complex, but it was good that we're able to do the institute measurement.
Yeah. That was what Tom, I mean, the paper you remember.
No. I'm only talking about, the paper, the recent paper I'm talking about.
Oh.
MIT, yeah.
Oh, MIT.
Yeah, just send me email.
I will,
I'll send
yeah,
it
yeah.
to you.
Thank you so much. The next time. We'll be in touch. I really want to.